thing, but it is what it is. So we said we are moving on to talking about the proof of the first theorem, right? Now, the idea with the first theorem is that the first keyword you need to know when you prove this theorem is congruency. Before we even start, let's just map the word proof of theorem 1 to the word congruency. Because if you can remember that, you're fine. You see, proof of theorem 1 equals congruency. Because remember, theorem 1, all it is trying to do is to show that these two are equal and that this is a 90-degree angle. Whichever one comes first, the other one has to follow. So with theorem 1, when you're going to be proving it, right, they give you a circle which has a perpendicular, two lines that are perpendicular. One is a chord, the other one is just a line from a circle. So the other thing is you need to know what a chord is, or you need to have an idea of like the different names of your different circles. Because if you know the different names of your different circles, the different names of your different lines, you're in a better spot, you see. So for example, if you have a circle, right, there is a circle, you see. So this circle, a chord is just a line from one point of the circle, all the way to the other point.
Never in the center.
Yeah, it doesn't have to be passing through the center. It just has to start from one point to the other. A diameter, though, is just a special kind of chord. Hence why it has a specific name, you see. It's called diameter, so it comes from one end to the other. A radius is not a chord, you see, because it does not touch the other side of the circle. But anyways, with proving theorem 1, the key thing is lines that are perpendicular to each other. So if you have lines that are perpendicular to each other, right, and one of them is coming from the center of a circle like this, if they were to ask you, let's put letters here, right? We said here A, B, C, and O. If they wanted you to prove that AC is equal to CB, that's more like them asking you to prove theorem 1. We said to prove theorem 1, you just need to remember congruency. Remember, congruency is a way of saying, is a word to say that two triangles are 100% identical. All the angles are the same, all the sides are the same. Everything is the same. That's congruency, right? Yeah. So all you're going to have to do is you need to prove that two triangles are exactly identical. So before you can prove that two triangles are exactly identical so that you can then say these lines are equal, you need to construct those triangles. You need to put lines in your sketch that will manifest those triangles, you see. So hence when you prove, the first thing is you construct two lines that make triangles. You construct line OA and OB, you see. It's part of your proof. You construct these lines. It is 100% legal. So obviously, maybe because of, maybe grade 10 work, something like adding something to a question for you to make it work is something that may not have been done before. But now you want to make it normal, especially for Euclidean geometry. You add stuff to your question that make it make sense, especially when you're proving, you see. So, and also sometimes when you just have to answer questions, you can construct a specific line for yourself so that it can help you to maybe like use a theorem. It's 100% legal. So here, they said here, what did they say here? So the thing is here they said now, let's see, they said here, we said we should construct these lines. That's the first thing. Now you need to state what you want to do. It's almost like a reminder for yourself, you see. You've constructed these lines. Now you want to prove, you see, you want to prove that OCA, or triangle OCA rather, is congruent to triangle OCB. OCB. You see? So that's what you want to do. As long as you can prove that these are congruent, you would have proven that AC is equal to CB. You see that? Yeah, because you would have proven that everything of these two triangles are identical. So the sides that match will be the ones equal to each other. The angles that match would be the ones equal to each other. So proving congruency, one thing you need to remember is just prove that any three things are equal except for three angles. I'll repeat. When you're working with triangles, there are two things that matter: angles and sides. You see, angles and sides. So for congruency, you just have to choose three sets of things that are equal, as long as you're not showing that all three angles are equal. You see, that's how you prove congruency. Any combination of three things, as long as it's not angles. It can be sides all three, but it cannot be angles all three. You get it? You can have two sides and an angle, or two angles and a side, or you can have three sides, as long as you just don't have three angles. Because proving that three angles are equal, that's a way to prove similarity. Obviously, with congruency, all three angles are equal, but it's not like a firm way of proving congruency, because three angles could be equal, but then it does not always mean that the triangles are congruent. Hence why using three angles to prove congruency does not work. It has to be three certain pieces of information where it's not all angles, you see. So with that being said, the first item you want to prove to be equal here between these two triangles, it's the blunt one. They both share the same side here. You see? So in these two angles, OC is equal to OC. Now, the other thing with Euclidean geometry is whatever you write, there has to be a reason. You see, if it's like a statement that is you, let's say, saying something based on knowledge. So you would be saying that this is equal for both triangles because it's a common side. You see, that's your reason, statement and the reason. So we need two more statements and reasons. The next one is another easy one. The lines here that you constructed. Remember, these were constructed strategically. They are both the radius of the circle. You see, OA is equal to OB. The reason is red eye. Red eye is a reason that is basically you stating that it's two lines that are both the radius of a circle. So any line from a center going to the edge of any circle, it will always be equal, always and forever. You get it? Yeah. So that's why these two lines are equal to each other. Lastly, right, you already know that this is a 90-degree angle. So you're going to use that to say that the other side is also 90 degrees, because angles on a straight line add up to 180. So you would be wanting to say that this is 90 degrees, and you also be wanting to say the other side is 90 degrees. You see. So what you can do for yourself is you visibly can see that this angle here, the way you're gonna name this angle, you can just call it angle OCB. You see, because you have O on one side, B on the other side, C in the middle. So it's called angle OCB. So what you wanna say is you wanna say that OCB is equal to OCA. So you just need to state that they are both equal to 90. You can state that they are both equal to 90 individually with their individual reasons. So the first one, you saying that OCB is 90 because they gave it to you like that. Remember, our sketch was initially given like this. You see, because they gave it to you like that, that's a reason for you to state that that angle is 90, because any statement where it's given to you, your reason would be that you are stating what you're stating because it's a given statement. You see, so here, OCB, you're gonna say OCB is equal to 90 degrees. How do you know that? Because it is something that is given. Now, this is something that is very normal, and it's one of the reasons you're going to use quite often. If you're given something, you write it as a reason when you use it. You see, given. So with you now saying that OCA is 90, your reason is not given. So you have to tell them why you're saying OCA is also equal to 90. So OCA here, you can say something like it is equal to 180 degrees minus 90 divided by 2. Now, your reason for stating that this is 90, you're just going to say here, angles on a straight line. You see, the key thing here is, firstly, angles on a straight line add up to 180, right? And the other side is equal to 90. You see, so no, did I just say divided by 2? No, man, that was just an error. The divided by 2 is not supposed to be there. I meant to say 180 divided by 2, but that's not as good as saying 180 minus the 90, because the 90 is already the other angle. You see, so 180 is where our reason is going to come in there to supplement where we got the 180. The 90, we clearly got it from our given statement. So you can just say this, 180 minus 90 equal to 90. So now you can see that we have two sides that are equal and two angles that are equal. So automatically we have three things that are equal, which is two sides and an angle, three sets of information. So now we can say, therefore, triangle OCA is congruent to triangle OCB. You see, and the reason for that is side angle. You found a side, you found another side, and you found an angle that is equal to the other triangle. So because of this statement right now, you can go on and say that, therefore, AC is equal to CB. You see? Now, for this statement, you can just say it like this, but to add a bit, a bit more oomph, you can just say corresponding sides of congruent triangles. There you go. Because I mean, like, the one side here matches with this side. The one side here matches with that side. The common sides here match, you see. Just like the angles. This angle clearly goes with that one. This one clearly goes with that one. And then the 90 degrees clearly go with each other. You see. Yeah. So that's theorem 1 and its proof. You see. The thing is, this is something that is fixed. So you can see that you just have to know it. So since it's still new like this is the best part, to sit down and actually just like memorize these things. It's not like cramming. Cramming and memorizing are two different things. You see, cramming is putting it into your short-term memory. Memorizing is putting it into your long-term memory. So you want to put this into your long-term memory so that it becomes like second nature to use it. Because I promise you, this year and next year, if you know Euclidean geometry, you easily have a good 33% on your paper 1 already given, because that's how big Euclidean geometry is. It's a third of your entire paper. You see, a third, 30%, 25% minimum. So it's a lot of marks. It's a lot of marks. So this is, if you want to put your effort into something this year for maths, do it now, since you're working with Euclidean geometry so early in the year. Yeah. So that's theorem 1. We can move on to theorem 2 now. But before that, do you have any questions on theorem 1?
No. Yeah, that one is the easiest.
Okay. Let's look at theorem 2. Because, let's just look at theorem 2, because theorem 1 basically has a converse also, which we spoke about. It's just a reverse. So let's move on to theorem 2 then.